Mastering Physics, Tutorial Weighing Lunch. For lunch, you and your friends decide to stop at the nearest deli and have a sandwich made fresh for you with 0.1 kilograms of turkey. The slices of turkey are weighed on a plate of mass 0.40 kilograms, placed atop a vertical spring of negligible mass and force constant 200 newtons per meter. The slices of turkey are dropped on the plate all at the same time from a height of 0.25 meters. They make a totally inelastic collision with the plate and set the scale into vertical simple harmonic motion. You may assume the collision time is extremely small. So, a couple of things. One, inelastic collision means that they stick and move as one object, which means loss of kinetic energy. That's going to be important. And then two, short time. The short collision time implies conservation of momentum, because what's going on here is the impulse due to gravity, which is what we'd have to worry about, is going to be the force of gravity times dt, but this is basically zero. So we can ignore that. There's no transfer of momentum from gravity during the collision, so we can treat it as if it were, well, a collision and not a weird complicated process. So on the next page, we'll sketch all the possible moments that we might care about. So let's draw a series of cartoons saying what's going on. In moment 0, we have the turkey of mass m1 hanging out above m2, in fact, a height which we'll call h above m2. We let the turkey go, and it falls until moment 1, which is right before the collision, so it's just before it hits the plate, and the turkey has picked up some speed v1, which we'll compute. Then, crash, bam, we have a collision. They stick together and move off with speed v2. And then finally, it has moved all the way to some distance where it compresses it to rest. At that point, it would be at its amplitude and reverse. One of the things that's been missing, though, is that when we add the extra mass here, when we go from here to here, the equilibrium position of this spring changes, because in moment 1, it's holding up only mass m2, but in moment 2, it's trying to hold up mass m1 and m2, but it will need to be more compressed to do that. So I'm going to say that the height of the plate beforehand, I'm going to call that a distance, which I call a distance s, above the new equilibrium point. So this height is the new equilibrium point. And then this motion will be plus and minus a above that height, about that height. So that's a little complicated. That last little bit makes it complicated. The first three things are pretty easy, and then the last bit is a little irksome. And we'll have to do that on the next page. Okay, so the first thing that happens is that the turkey falls through a height h, and it's not interacting with anything but the Earth, so we can just use energy conservation and say that the energy when dropped is the energy right before the collision. And so, well, where is it? Well, remember that we're going to set our 0 point and such at the new equilibrium position of the spring, so that we find out that the original position is all potential energy, and it's mg, in this case m1 g times h plus s. And then at moment 1, it has a half m1 v1 squared, that's its kinetic energy, but it still has some gravitational energy, which would be mgs. And we can notice that right away, this s and this, they're going to cancel. So it didn't really matter at this point that we had done that, but it will be consistent for later, and that's probably pretty good. So we're left with that mgh equals 1/2 m1, gh equals 1/2 m1 v1 squared, or V1 turns out to be the square root of 2GH, which is really quite common, and we probably should have expected the whole time anyway. So in principle, we could compute that velocity. Based on the numbers given in the problem earlier, that velocity turns out to be 2.21 meters per second, and that might be useful later. Between moment 1 and 2 is the collision itself, the crash bang that happens here, and we have to remember that we can't use energy conservation more because energy is not conserved in inelastic collisions. We know that some of the energy goes to deforming the two objects. If energy were conserved, the turkey would bounce back up with the same speed, and we would be in a whole different problem, and probably a whole different universe. But this isn't so bad because momentum is. So we can say something like m1 v1, the momentum right before the collision, is equal to m1 plus m2 v2, the momentum right after the collision. And so v2 is going to end up being m1 over m1 plus m2 times v1. And if we grind out those numbers, it's about 0.44 meters per second. Okay, here's the actual tricky bit, the subtlety. We are able to conserve energy again between moments 2 and 3. There are no distributive forces, but we have to be careful that we count for all the energy. And most importantly, this object is both a stretched spring and it's moving. And we want to end up to where it is some distance below its amplitude, right? It's moved down some amount. My picture here is horribly not to scale. And it's at rest. So we're going to say that the energy in 2 is the energy in 3, but the energy in 2 is both the kinetic energy and whatever's in the spring at that moment, and the energy in 3 is just potential energy. So we need to figure out where we are. In other words, we need to know what is that distance s. But that's not too bad. That's the amount of compression we get by adding one m1 to the thing. In other words, the spring needs to exert more force than it did before. It now needs to exert an additional force, which is the weight of one object, and that's going to come from the spring force, which is k times the stretch, the additional compression we do, really, how much the spring is outstretched beyond its equilibrium length. And so we can find that that means that the stretch, or really the distortion, is mg over k. And if we were to look that up, we would get, grind out those numbers, it's 0.0049 meters, which makes it pretty easy to go back to the energy equations and say, well, then we have 1/2 m1 plus m2 times v2 square plus the potential energy of that, which is 1/2 k s square, and that's going to equal 1/2 k a square. And from here, we have s. We can compute k2 to be 0.049. And then it is sort of just grinding it out. And to be entirely honest, I did it through a spreadsheet. I think that the actual trying to do this on a calculator proved to be pretty clumsy, and I will link to that spreadsheet if you want to see how that's done. I'm not using spreadsheet functions, I'm just being able to name my variables in Google Sheets, which is nice. If you do that, you end up getting that the amplitude is 2.27 times 10 to the minus 2 meters, which is what, 0.0227 meters, or 2.27 centimeters, which is certainly not unreasonable. Drops about an inch. Yeah, if you drop that much turkey on a thing, you might get about an inch. That seems reasonable. And then sort of quickly, we can do the other part in the problem, which was just to say, what is the period of oscillation. But this is almost embarrassingly easy because we know that the period of oscillation is 2 pi root m over k. The k we know that was given. Which m? The entire m, m1 plus m2. So if we grind that number out, we get something like 0.314 seconds, which looks to be 1/10 pi. And there might be some clever reason why that's the case, although I don't really see it, but it might be. Anyway, there we go with that problem.